If we're going to look out into the universe and try to explain what we see out there, we're going to have to measure it. And in that measurement process, come up with values for things. Now, it turns out that just having a value by itself sometimes isn't enough. Sometimes you need a direction to go along with that. And here's an example to help explain. Imagine I told you I climbed into my car and I drove at 10 kilometers per hour for 2 hours. What do you know about where I've ended up? Well, let's have a look and see what might be the case. So here I am in my car and I drive along at 10 kilometers an hour for 2 hours. There I go. And you might think, that's pretty clear. He went along for 2 hours. I should be able to figure out where they've gone. But here's another thing that might have happened. I might have hopped in my car and driven along for 2 hours, first doing this for 1 hour, heading along, and then maybe I did this for an hour. You can see I've ended up somewhere different. Maybe I did something completely different completely to that. Maybe I did something like this, and I drove around in a circle for 2 hours. So there wasn't enough information in that 10 kilometers an hour for 2 hours to really know what's happening. We need a better description. If we have a direction there, if for example I said I was at 2 kilometers per hour heading east for 2 hours, then you'd know exactly what was going on. It's clearly that first example just at the top there. If I was going at 10 kilometers an hour east for 2 hours. Now I have additional information. So knowing how fast I'm going and what direction I'm going in allows us to have a proper description of the situation. That's what we need in physics. We need the best description we can have. Now a quantity that has a size and a direction we call a vector quantity. And there's lots of examples of them. We just saw one there. That's an example of velocity, how fast you're going and in what direction. The vector quantity, velocity. Not everything's a vector quantity, by the way. You can think of some immediately. Say a 5 kilogram block. It has a mass of 5 kilograms, but its mass doesn't point anywhere. It just has 5 kilogram mass. Or time. In this problem I mentioned that I drove for 2 hours. That 2 hours didn't point anywhere. That 2 hours is just a unit of time. And so time is again a quantity that doesn't need a direction. We call quantities that don't need direction, that just have a number, we call those scalar quantities. So now we have two kinds of quantities, vector quantities and scalar quantities. We need to be really careful when we're doing our calculations that we know which of those quantities we're dealing with. Sometimes we only want to have the magnitude of a vector. That's okay. For example, you might only want to know the speed that something is travelling. The speed is the magnitude of velocity. They're not the same thing. One points somewhere, one is just a number. But how can we do calculations with these vector quantities? Well, one way we can think about them is to use an arrow to represent the vector. The length of the arrow tells us about the magnitude, and the direction the arrow points tells us the direction the vector points. So let's try some examples now where we're going to draw vectors as arrows and maybe do some calculations using them. I'm drawing an arrow here to represent a vector. You can see the arrow there is 6 units long and it's pointing off to the right. This might represent, for example, a velocity of 6 meters per second to the right. It has a magnitude and a direction as indicated by the arrow. Now I'm going to draw a second vector along here. You can see the second vector here is going to the right and upwards. This vector here, as you can see in the top left corner, goes across 5 units, x, and up 3 units, y. And we call those things the components. This has a component in the x direction of 5 units and a component in the y direction of 3 units. Now what if I wanted to add these two vectors together? I wanted to add, say, two velocities. How do I do that? Well, of course, I have to take the direction into account, and the arrows are doing that for me. What I can do now is I can pick up one of the vectors, for example here vector b as it's labelled, and I'll move it across so that the start of vector b is at the end of the first vector, vector a. And now my vector sum, the addition of these two vectors, starts at the beginning of a and ends at the end of vector b. So if I select these two vectors, making a blue arrow and b a green arrow, then I can say the sum of those, a plus b, is now indicated by that red arrow on there. And you can see it starts at the beginning of vector a and ends at the end of vector b. You can see it has a magnitude, it's quite large, and it has a direction. And the direction is different to the direction of a and the direction of b. Now what if I wanted to take the difference of two vectors? This is quite a common problem in physics where we want to find the change in a physical quantity. The change in a quantity is the final amount minus the initial amount. And that's the final vector minus the initial vector. Now, how can we do a subtraction of vectors? Say, for example, here, a minus b. Well, what we do is we have another vector that we think of that actually represents the negative of the b vector, a minus b vector. And I can draw that now. It looks kind of like vector b, but it points in the exact opposite direction. It's the same length as vector b, but it has the opposite direction. And it's labelled on this little program here as c, but we'll think of it as the vector minus b. And if I want to do a minus b, then I pick up my vector here, minus b, and I add it to vector a. So now I've got vector a shown here in blue, vector b shown here in green, and I want to do a minus b, so I'll click on the a minus b button, and you can see I get the red arrow there again that starts at the start of vector a and finishes at the end of minus b. So there's how you subtract two vectors, often to find the change in a quantity. Now this is a little complicated, and we can make it quite a bit simpler if we restrict ourselves to working in only one dimension. And a lot of the problems that we'll be doing in this subject will only be in one dimension. That means instead of worrying about x and y directions, we might only worry about the x direction, for example. So here I might draw one vector, vector a again like that. A second vector, for example vector b, still points along the same line. In this example here, vector a in blue is a positive vector. Vector b still has a direction. It's now a negative pointing vector. And so now when I want to combine these numbers, these vectors, for example, a plus b, I take a positive value for a, and the negative value of b tells me its direction. So a plus b would be a positive number plus a negative number. The direction is being taken into account by the positive or negative sign of the number. And this can make things a lot more simple than they are in 2 or 3 dimensions. And as I say, a lot of the time we'll be restricting ourselves to one dimension. Now that we know how to do these vector calculations, we're going to, in the next topic, use them to understand how things move. We're going to look at where things are, how things change where they are, and just as importantly, how they change where they are.